I'm going to show you today about how to do atomic orbitals, how to write out atomic orbital configuration and something called electron configuration and another one called noble gas configuration. And the PowerPoint has some of the information. After this, I have a couple videos I made with a scanner, so I get to be a hand model. All you get to see is my hands. But you also get to hear me explain it. And one thing you guys will need to do is I have a periodic table. You probably already have, but you need to mark it all up. So I'll put another one on there in case you download it and put the information. You'll see that when I do the next video. Okay. But again, when we're doing atomic structure, hydrogen consists of the nucleus and one proton, and it's in the first row. It's the first element. It has one electron, so it's in the first level, one, and it's an S because the first two columns are all S's. Okay, so how are electrons treated and more complicated? Well, it's easy, like I said, with the simple ones. But what we need to do is, as we move along, we have to follow rules for filling in those the guidelines for filling in electrons. The first one is every orbital holds two. Okay, when you get to the third one, you got to go to a new orbital. Okay, you can't keep just throwing them in there and throwing them in there. Okay, the electrons always occupy the lower orbital energies first. So in other words, when we do these, we always do them in the same order. Okay, we always start at 1s. We start at hydrogen. Then we go to helium. Then we go to lithium. We always go in the same order. Okay, the S's first, the P's, the D's, and the F's. They always go in that order. And the reason why they do that is, I don't know if the rule's on here. No, I don't have it. But there's a rule called Aufbau's principle. An Aufbau's principle says all electrons go to the lowest energy level first. So you fill the lowest one first, and then you can move up, and then you can move up. But you can't go to level 3 unless you have level 2 filled. You can't have level 2 filled unless you have level 1. Okay, so each orbit in a sublevel must contain electrons before another electron can be added. And again, I'll show you that one. That's called Hund's rule. Okay, so when you're looking at orbital diagrams, this is an orbital diagram. I just do a line with arrows because drawing all these boxes would drive me crazy. But what this is saying is in the 3p orbital, we have two electrons, one spinning this way, one spinning that way. Okay, that's an orbital diagram, and I'll show you how to do those again. And there'll be a video after this one to show you exactly how to do it. So this is the orbital diagram for hydrogen, 1s. And again, I just do a line, I don't do a whole box. I have my one electron, it's in the 1s orbital. This is the electron configuration. Instead of writing 1s with an arrow, you just write 1s1. You use like an exponent to tell you how many electrons are in that. Okay, here's helium. Now helium has two electrons. So we got one here, now we got one going down here. And then it's 1s2. And this, when you add up the exponents, they will, if they don't equal the atomic number, then you did it wrong. Okay, here's lithium. Okay, I filled in my 1s. So now I got to move on to the next level. And if you follow your periodic table, lithium's in the second row in the S. So it's 2s and there's 1 in there. And then if I rewrote this as electron configuration, be 1s2, 2s2. And if you notice, if I add these together, I get 3. That's the atomic number of lithium. And there's beryllium, the next one. You can't see the electron configuration, but it says 1s2, 2s2. Sorry about that. But again, I have to add one more in there because it has one more electron. Okay, when we get to boron, now there's a goofy thing going on because once you skip over the S's, the first two columns, and you go on to boron, it is in the P's. And now when you have P, there's 3 sublevels, okay? There's 3p orbitals because it holds 6 electrons altogether. When you put these in, if you look at this one, you don't put them in together and then leave these ones blank. Instead, you just put one in the first one, you would put one in the next one, and if I'm doing the next one, which is nitrogen, I put one over here. That's called Hund's rule. And Hund's rule says when you have orbitals of equal energy, electrons go in one at a time and they don't double up till they have to. I call this the apartment rule. If you have 3 people and you're looking for an apartment, you get a 3-bedroom apartment, you each take your own bedroom. Why should you have 2 in one room and 1 in empty rooms? So you use the space that you have. The other thing is you have to write them out. Okay, if I left these off, because remember we do electron configurations to show you where the electrons are. This, if I do it right, I have room for 5 electrons. If I leave these guys off, I only have room for 1, when I really have room for 5. So again, this is like the apartment, a 3-bedroom apartment. If only one person's living in there, doesn't mean these rooms aren't available. They're just not being used at the time, but they're still there. So when you get to a new level, make sure you write down all of them. Okay? So this is carbon, and again, 1s2, 2s2, 2p, 2, okay? And then when you get to nitrogen, again, one at a time, okay? Note that the electrons are in different orbitals. They say rule 3, and that's Hund's rule, H-U-N-D. Hund was a guy that said, hey, the orbitals go in one at a time. Now, when you get to oxygen, now because you have one in each, now you have to double up. It'd be just like you have 3 in a 3-bedroom apartment, and you take on another roommate to save a little money. Well, somebody's going to have to double up, okay? But they don't double up till they have to. Okay, so this would be oxygen, and then fluorine, and then neon. Okay, now they're all full. And again, this is called the orbital notation. This is called the electron configuration. If you count these up, you have 10. That's the atomic number of neon. If you count these up, you have 10. That's the atomic number of neon. So you got to say where all the electrons are. Okay, here's all of them, the ones we just went through. And again, it shows you the these are the atomic orbital diagram, and these are electron configurations. The thing to remember is we just do lines. We don't do boxes. If you want to do boxes, please, but I do lines. And again, I'll show you that in a little bit. Okay, once you go after that, then you go to sodium, which would be in the next column, 3s. And again, the s's, there's only one. When you get to the p's, there's 3, so you have to draw all 3 of them. Okay, so when you're doing electron configuration, what did they go? Oh, here's sodium, and here you see magnesium. And then aluminum, you skip over to the p's, and then again, you fill them in one at a time. So this shows you the configuration all the way up to argon. But again, if I'm starting with sodium, I have to start at 1s. I always have to do 1s, then 2s. Then 2. The order always stays the same. It never changes. The only thing different is where you stop. That's when you get to your element. But the order never, ever is different. Okay? When you're looking at these, sometimes you're looking at the electrons in the very end, in the S and the P, are what they call valence electrons. And they're the ones in the very outer energy level. They're the ones that are involved in bonding. And next chapter, when we do Lewis structures, they're very important because they're the electrons that are going to form compounds. Okay? And you can tell, like oxygen has a 2 and a 4, it would have 6 valence electrons. Well, if you look on your periodic table, if you do the first column, like sodium down or hydrogen down would be 1. And then after that, you have boron down. Those are 2. You skip over the transition because they're different. Then you go over to boron down. Those have 3. And then they just go in order 3. And then carbon down has 4. Nitrogen down has 5. Oxygen has 6. All the halogens, fluorine, chlorine, bromine have 7. And then you have your noble gases. They have 8. And that's how you figure out how many valence electrons they have. It's actually really simple. It's either their A thing, and if you don't have A on your periodic table, let me see. The one I have has no numbers on it, but I'll show you if you can see it. Okay, here's hydrogen down. They all have 1. Here's beryllium on down. They have 2. Then you skip over all this middle stuff. Go over here to boron. Now I'm trying to see if you can see that. Boron, these guys all have 3. Then carbon down has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And then the noble gases have 8. And again, I'll show you those. Next chapter, we're going to do that. We need those numbers, but I'll also show you on the videos after this. Okay. So how many valence electrons does phosphorus have? Go to phosphorus. Phosphorus is in group 5. I'm looking at the periodic table. It's in 5A. It's in the 5th column, so it has 5. It's that simple. The max number for valence electrons is 8. You can't add more. If you did it from the configuration, you'd notice the S's and the P's. There's 5. Okay. All right. Which element would have this configuration? It ends at 3p6. This is the easiest way to do it. You guys go 2, 4, 10, 12, 18. The atomic number 18 is argon. Okay, that's the easiest way when you're trying to find an element is just add up the exponents and that equals the atomic number. Okay, you can go to the column, but sometimes they get a little messed up. Just add the exponents is by far the easiest way to do it. Okay. Okay, your electron structure of the atoms relate to their positioning on the periodic table. This tells you everything. And again, I want you to run one of these off. I'm going to show you a bunch of stuff to write on it. And if you have that, it's really easy to do these configurations. And again, that's in the video after this. I keep talking about that, sorry. Okay, whenever they started making the periodic table, Mendeleev, remember I told you, was the guy that gets credit for it, but there was another guy by the name of Meyer. He did kind of the same thing. He just wasn't as vocal. He wasn't out there, advertising what he had done, so he doesn't get it. But they proposed, when they started doing the periodic table, they organized the elements, and they used a lot of the valence electrons. They didn't know it at the time, but their characteristics are very similar. So when they started organizing them, they found out that, hey, lithium, sodium, potassium, they all have similar characteristics, so they put them in a column. Well, now that we know that they have one valence electron. And then with the second column with beryllium, magnesium, calcium, yeah, I'm cheating, I'm looking at them, strontium, they react with the same things. It turns out they have two valence electrons. So when they were setting up their periodic table, originally they put them on an increasing atomic mass. Later on, they fixed it and they put it by atomic number. But really, their column, they're very similar to each other, and a reason for that is the number of valence electrons. Now, when we do valence electrons, we do the first two columns, and then we skip over to the last 6 columns. These guys in the middle and down here, they don't really follow a pattern, so we don't put them in that category, okay? But when these guys were organizing that periodic table, when they did all that stuff, it boils down to, by putting them in similar characteristics, is because they have the same amount of valence electrons, okay? The next part, I think, talks about periodic table, and right now we want to concentrate on those configurations. So there'll be 2 videos after this that I want you to watch. Again, I'm showing you, I talk it through and you can see me drawing them out, the configurations, and then I want you to do a couple problems, and then we'll pick up the end of this chapter. We'll talk about more about the periodic table. So that's it for now.